Okay, good evening. Week 8, Thursday. We're going to still carry on our example on combined loading, and I'm going to do uh, examples on or lecture on principal stresses. I like to highlight that there's no quiz for this week, okay, but there will be one next week, okay. So this example over here, we did it. We did this example on Tuesday, but we've not completed it yet. Okay, so we are given a structure as shown, and it has a destination of W200 times 41.7. So this is the information that is given. So we are going to follow the geometry of this specification. Okay, so these are the information that we need for calculation that I highlight on Tuesday. So I have completed looking at the stresses at point A. Okay, this one we have done. So we are now looking on normal and shearing stresses at element B. Okay, and element B. And if you look at the lecture on Tuesday, right? This is our lecture on Tuesday. We have completed looking at the normal stress on element B, and we found that it's minus 14.948 times 10 to the power 6 Pascal. Okay, so let me write this down. So we found that on element B, the normal stress in the Z direction is equal to minus 14.948 times 10 to the power 6 Pascal. Okay. So the next thing that we are going to look at is the shearing stress. Okay, so shearing stress. So due to Vx first. Okay, shearing stress due to Vx. So we look at this cross section over here, right? So Vx, if we look at the x direction, so what are we looking at? So if we look at the transformation of the geometry over here, so this is x, this is our y, and this is our z. Okay, so we are going to look at Vx. So we know that Vx is 16 kilonewton. Okay, so 8 per side. And element B is down here. Okay, so this is our location of element B, right? So now we sketch our shear flow, right? So it's a white flange. So all these dot points I'm drawing down here, all our terminals. Okay, and this one is also our terminal because the shear flow meets at the center and has nowhere to go. Okay, so what we can see over here, if we look at the formula, okay, so we're looking at the shear stress, right? Shear stress and the intersecting plane last on Tuesday we talked about is in the Z, and the shear is in the Y direction, is equal to Vx over Iyy Qy over T, right? So for this case, okay, Qy at point B, element B, is equal to 0. Y is equal to 0 because at point B, right, at point B, yeah, at point B, At point B, it is a terminal. Okay, so I did this on Tuesday also, because the shear flow from the top, okay, the shear flow coming from the top portion and coming from the bottom portion meet exactly at the center, right? So it cancel it off. Okay, so the shear stress is equal to 0. So you can write that the shear Z Y is equal to 0. Okay, so this is the easy part. Anything is equal to 0 is so much easy to calculate, but you have to know why it is equal to 0 more important than anything else. Okay, now when doing this, I think I have to put in what we did is we did thin wall analysis. Okay, wide flange. So it's not a box beam, okay? We did a wide flange analysis, okay? All right, so the next one, we are going to look into shear stress or shearing stress. Due to Vy, okay? So now we look at our Vy. So let me draw as element B first. So this is our element B. So Vy, okay, so y direction. So this is our Vy is coming at 25 kilonewton. Okay, then we now design our shear flow direction. These are our terminals. So we know that for Vy, right, we are also using thin wall analysis. Thin wall analysis. Wide flange. Right, so it's only Q. So over here, the formula we're going to use is the shear stress, right? The plane intersecting transformation on the z-axis, the shear flow will travel in the y direction is equal to Vy over Ixx, right? Qx divided by T. Okay. So for this case, we know that let's gather what we know. So what we know is Vy is equal to 25 times 10 to the power 3 Newton. We also know that our Ixx, so we look under the table, we look at Ixx is 40.8 times 10 to the power minus 6. 40.8 times 10 to the power minus 6 meter 4. And then our thickness, so thickness over here is thickness of the web, TW. So thickness of the web is 7.24, as you can see down here. Right, so 7.24 times 10 to the minus 3 meter. So the next thing is the Q for our point B. Okay, so Q on the x-axis at point B is equal to Q first moment of area about the x-axis of the flange plus Qx of the web. Okay, so the area of interest is I'm highlighting in yellow. So this is the flange and this is the web. Okay, so it's the entire area. So the x, so is IXX, so this will be our width, and this over here will be our depth. Okay, so like what I tend to do is the Q, I tend about the x-axis, I tend to do width multiplied by depth multiplied by y bar. So that's the general formula that we're going to use. Right. So for the flange, the width is our BF. So BF over here is 166. Okay. So width, our depth is the thickness of the flange. So thickness of the flange over here is 11.8. Right. And then the y bar, right? So the y bar is the distance from here to here minus by the distance from here to here. Oh, hold on. So it's the individual centroid of the flange. Okay. So this is equal to 11.8 times 10 to the power minus 3 divided by 2. And we need to find D. The depth is 205. Okay, so this over here is 0.205 divided by 2. So this dimension over here, this is your y bar. Okay. So from here, we have 0.205 divided by 2 minus by 11.8 times 10 to the power minus 3 divided by 2. Then plus by the web. Okay, so the width of the web is 7.24 times 10 to the power minus 3. Then the depth is equal to 0.205 divided by 2 minus 11.8 times 10 to the power minus 3, right? So this is our width, depth, and then the y bar is 0.205 divided by 2 minus by 11.8 times 10 to the power minus 3, and just multiply by half. Okay, so that is the section. So the section, so this is our web. So this is the y bar now. Okay, right. So let's calculate what we have. So 0.205 divided by 2 minus 11.8 power minus 3 divided by 2 times by 11.8 power minus 3 times by 0.166. So it's 189.22. Okay, times 10 to the power minus 6. Let me do it again. 0.205 divided by 2 minus 11.8 power minus 3 divided by 2 times by 11.8 power minus 3 times by 0.166. 189, yep. And then plus 0.205 divided by 2 minus 11.8 power minus 3, the whole thing squared, times 0.5 times by 7.24 power minus 3 is equal to 29.780. So let me do it again. 0.205 divided by 2 minus 11.8 power minus 3 squared times by 0.5 times by 7.24 power minus 3, 29.780. So the first moment of area 189.22 plus 39.78 is equal to 219 times 10 to the minus 6 meter. 219 times 10 to the power minus 6 meter cube. So therefore, I'm just going to write down here Okay, so therefore